Hi, everyone. Good morning, good afternoon, or good evening, depending from which part of the planet you are currently joining this live stream. It's 5 p.m. here in Austria, in Salzburg, where I'm located. And yeah, I would like to wish you a pleasant day and hope that you're going to join this webinar about data modeling in Power BI. Before we start, a few introductory sentences. First of all, we will have amazing moderators in the chat. So Johnny and Pragati will be there to assist with your questions. And since I mentioned questions, please ensure that you always prefix your questions with capital letter Q, so that moderators and I, during the chat monitoring, can also you know, easier find your questions and try to address them. Uh, Other than that, few more housekeeping rules. Since we are going live and we have people joining from different backgrounds, different cultures, and so on, please be mindful and respectful to everyone, and ensure that everyone feels welcomed and convenient here during this live stream. I would really appreciate that. As yeah, as a starters, maybe I saw that some of you already introduced yourself from which part of the world you are joining. So maybe as a starters, you can share your location, like city or country, of course, if you like. If not, that's also totally fine. Okay, so let me just arrange my screens and start while we are all here today to learn about data modeling, and specifically about data modeling for Power BI. So just before we start, a brief introduction about myself. My name is Nikola. I'm originally from Belgrade in Serbia, but for last almost 9 years, I live in wonderful city of Salzburg in Austria, where I work as an independent data platform consultant and trainer, focusing on mostly on work with Power BI and Microsoft Fabric. You can find me on web, data-mozart.com. That's where I'm blogging as much as I can, as frequently as I can. I also have my own learning platform, learn.data-mozart.com. I'm also active on social media, so yeah, feel free to connect if you like, and stay in touch. Other than that, what I would like to emphasize here is that it's almost done. The book Fundamentals of Microsoft Fabric that Ben Weissman and I wrote together for O'Reilly, it's almost there, so you can expect it in next few weeks, or at least, let's say, month or two, to be published. So I see we have people from all parts of the planet. Groningen, Netherlands. Hi, we have Belgrade, Madrid, Barcelona. Oh, okay, you are my favorite for today. Vienna, Munich, Basel. Amazing. Sunshine, Florida. Yes, I'm not jealous at all. Okay, so nice. Thanks everyone for sharing. And yeah, as I already mentioned, we have Johnny and Pragati here with us in the chat. They will try to support, and I really appreciate, because they are doing this in their spare time. So one huge shout and a round of applause for both Johnny and Pragati, and huge thanks for helping with this webinar. So what are our session goals? Usually, whenever I do those kind of live streams, live trainings, live sessions, I have two main goals for people that are joining. Obviously, you are here to learn, right? So that's the main reason why we are here, but also to have some fun. So I'll try to, make this learning experience as entertaining as possible. So yeah, you'll tell me afterwards in comments if we managed to do that or not. But that's my expectation. That's my hope. Pomože Bog, Bogdane. I see people also joining from Serbia. So yeah, United States, India. Yeah, amazing. So a short introduction about the topics that we are going to cover today. The initial plan is to stay and cover all of these topics, including demos and everything, in approximately 2 hours. Now we'll see if it's going to be below that or above 2 hours. But there is nothing strict. So this is my own channel. We are very, very flexible with the format and structure of this session. So let's make it useful for all of you. So we will first discuss data modeling concepts in general, something that you can apply not only when working with Power BI, but more generic data modeling concepts that are also relevant if you use other tools or if you plan to leverage these skills by using other tools. So we'll explore concepts such as conceptual model, logical model, and physical model. So those are three main parts, three main stages in the data modeling process. Then we will discuss the differences and use cases for so-called OLTP and OLAP. So OLTP, as you will learn later, stands for online transactional processing, whereas OLAP stands for online analytical processing. And depending for which of these two you are building your models, there are some subtle differences in how you should structure your data to get the most out of the models in each of those two scenarios. We will also cover two concepts that are relevant in all eras, all tools, and all scenarios: normalization and denormalization. Of course, just a short introduction. I believe normalization can be like, yeah, one day one day of full training. But yeah, today it's just a short introduction. And then we will skip into the wonderful world of dimensional modeling, where there are a lot of things to cover. We'll start by explaining what are fact tables and dimension tables, what is the main difference between these two. Then we will explore the concept of granularity, one of the key concepts in dimensional modeling. Then we will talk about the differences between the star schema and snowflake schema in dimensional models. And then we will explore various concepts, various techniques that you will face sooner or later once you start working not only again with Power BI, but also in Power BI. So things like role-playing dimensions, how to implement them specifically in Power BI, what are the available approaches. We will talk about slowly changing dimensions, how to work with fact tables that have different granularity in your semantic models, and also to explore more about relationships and specifically about filters, because filters are one of the key concepts in Power BI. Then we will wrap it up by exploring different use cases or scenarios for use as self-service data modelers, and how can you leverage all of these concepts and all of these skills using Power BI only. So in case you don't have access to the underlying data source, what are your options and how you can properly build your Power BI semantic models using only Power BI as a tool of choice. So you don't need to go anywhere outside of Power BI. Fine. So yeah, when teaching these data modeling concepts and techniques, I find one of the concepts particularly intimidating for many data professionals, especially those who are just starting their journey. And that is the concept of data modeling in general. Why is data modeling sometimes so intimidating? Maybe because you see all these diagrams that look so complex and complicated. But data modeling is not about the diagrams. Don't think about data modeling just as diagrams. It's about creating trust. And when I say trust, I talk about shared understanding between the business and data professionals with the final goal to provide increased business value with data. So if we agree that data modeling is about creating trust, I believe we can also agree that trust cannot be easily built, right? A certain amount of time, a certain amount of effort should be also taken into consideration. And time and effort are not something that you take for granted. It's something that you need to invest. So we can rightly assume that data modeling is kind of an investment that should bring more stability and more flexibility to your business in the end. Think of it like investing in building the house. Obviously, you can choose to go the quick and easy way by simply putting building blocks directly on the ground, and it can possibly work just fine for some time until some new circumstances occur. Think about an, I don't know, earthquake or thunderstorm, for example, and then your house will be damaged. But it's not only the house that's going to be damaged. Your trust will also be damaged. So people who live with you in that house, your neighbors, your friends, will realize that you didn't invest the proper amount of time and effort in advance to prevent such a bad scenario. Now let's assume that you decided to take another path, more demanding at the very beginning, which will require more time and more effort from your side, and you established a proper foundation for the house, secure things under the ground, and then build a house on top of it. Now your house will be more stable and can adapt to future problems and future challenges. Since we explained why it is of paramount importance to invest time and effort in building a data model, let's examine those three main data types of data models and how they fit into this big data modeling picture. This is a brief overview of key characteristics of each of these data model types. So let's start with the purpose. You already or you will learn that conceptual data model should provide a 10,000, let's say 10,000 feet high overview or perspective of the business entities that are of particular interest. On the other hand, logical data model puts these entities into a logical structure, assigning them specific attributes and defining how these entities are connected between themselves. Finally, we have a physical data model, which represents a low-level detail of how the data will be physically implemented in the database to ensure the optimal performance and efficiency. The target audience for the conceptual data model is not only data professionals, but also business stakeholders. Logical data modeling involves data engineers, data architects, and data analysts, while physical implementation should bring also in database administrators and database developers. Finally, don't forget, and I think this is very important, that first two stages, so conceptual data modeling and logical data modeling, they are platform agnostic, whereas the final stage, physical data modeling, requires choosing a specific platform and specific technology. So let's go and examine those three stages of building a data model in more detail. Usually the starting point in data modeling workflow is creating a conceptual data model. This is a high-level perspective on the business needs for different types of data. As we are talking about a high-level perspective, the main goal of the conceptual model is to simplify business processes and entities which are important in day-to-day business workflow. In this stage, we are compiling a big picture, like what are the key entities in our business workflow? How do they correlate to each other? The key characteristic of conceptual data model is that it should communicate in easy to understand terms. Don't forget, we don't talk just to data professionals, we also talk to business people. They don't always understand these technical terms and phrases. Simply said, you should leverage a common language that business users and non-technical individuals can easily understand. Okay, I know I told you that data modeling is not about diagrams, but still we need to visualize the process of creating a data model. And I'll give you a very basic example of the conceptual data model. In this illustration, you can identify various entities: stadium, event, customer, attendee, and ticket. You may also notice how these entities are interconnected. This high-level overview provides a kind of a simplified picture of the business workflow within the organization. So let's go and examine all of these entities and how they are basically structured from a conceptual point of view. Our first entity is stadium. Stadium has a name, is located in specific country and city, which uniquely identifies that stadium. Stadium may host many events, and there can be many attendees coming to these events. Then the next one is event. A specific event cannot exist outside of the stadium where it is scheduled to be held. And an event can be attended by an attendee, and there can be many attendees for one event. So you see how I'm explaining these concepts that will later become part of the model. I'm explaining this in natural language without using any technical phrases like we will use one-to-many relationship or something like that. So I'm just talking to you like what can be done with this specific entity. The next one is attendee. Attendee is the entity that attends the event. They can also be a customer of the stadium entity in case, for example, if they visit a stadium shop or similar. The key difference between the customer and the attendee is that the customer doesn't necessarily need to attend a specific event at the stadium. They can just come visit the shop and they are our customers. Customer may also have a relation to stadium. Like I said, for example, by visiting a stadium museum or buying at the stadium fun shop, for example. But that doesn't make them attendees of the event. So there is a difference between customers and attendees. And finally, ticket is an entity that represents confirmation that the attendee will attend a specific event. Each ticket has a unique identifier because, yeah, it would be really awkward if two or more attendees get a ticket with the same number, right? Although the ticket is uniquely identified, one attendee can purchase multiple tickets. Now that we've explained the core components of conceptual data modeling, you might be wondering, why is this important? Why should someone spend time and effort describing all these entities and relations between those entities? Remember when we're talking about building trust between business and between data people in your organization. That's what the conceptual data model is all about. Ensuring that business stakeholders will get what they need explained in a common language so that they can easily understand the entire workflow. Setting up a conceptual data model also provides business stakeholders with the possibility to identify a whole range of various business questions that need to be answered before you start building a physical data model. Sometimes it's too late, especially with all these business users asking various types of questions all the time. Yeah. Additionally, conceptual data model depicts sometimes very complex business processes in very easy to consume way. So instead of going through pages and pages of written documentation, someone can take a look at the illustration of entities and relationships, all explained in a user-friendly way, and quickly understand the core elements of the business process. Once the business and data teams align on the conceptual data model, the next step in the data modeling process is designing a logical data model. In this stage, we are building upon the previous step by identifying the exact structure of the entities and providing more details about the relationships between these entities. In this stage, you should identify all the attributes that are of interest for specific entity, as well as relationship cardinality. So now we are going into these nitty-gritty details. Please pay attention that same as for conceptual data modeling stage, we still don't talk about the specific platform or specific vendor or specific solution. The same as with conceptual data model, our focus here is on understanding business requirements and how these requirements can be efficiently translated into the data model. There are several steps to be performed to ensure that conceptual data model successfully evolves into the logical data model. First one is identify entity attributes, then identifying candidate keys. This means find out which attribute or set of attributes uniquely identifies a specific entity. Choose primary keys. Based on the findings from the previous step, set the primary key of the entity. Don't worry, we will talk about primary keys very soon. So if you don't know what primary key is, just stay tuned. Apply normalization or denormalization to the data model. Again, we will discuss normalization and denormalization in more detail later in this webinar. At this moment, keep in mind that normalization should eliminate data redundancy and is very common in OLTP systems, which we'll also talk about very soon. On the other hand, denormalization is the opposite process. It's predominantly used in analytical systems or OLAP systems to minimize the impact of join operations, and speed up data reading process. Set relationships between entities. This means validate how various entities interconnect and, if needed, reduce the complexity of having multiple relationship dependencies by breaking down one entity into multiple entities if necessary. Identify relationship cardinality, another extremely important step. So relationship cardinality defines how many instances of one entity are related to instances of another entity. There are three main cardinality types: one-to-one, one-to-many, and many-to-many. We'll also explore this from the Power BI perspective, but it's also applicable to other tools. Iterate and fine-tune. In real life, it's almost impossible to find a data model that suits everyone's needs and fulfills all the requirements immediately. That's not going to happen. So it's of key importance to always ask for feedback from business stakeholders, and based on that feedback, fine-tune the logical data model before materializing it in the physical form. And our last step in data modeling process is physical data modeling. That's this basically final touch. So how the data model will be implemented in the specific database. So unlike conceptual and logical data models, which are platform and solution agnostic, physical implementation requires defining low-level detail that may be specific for the certain database provider. Okay, so you decide you go with, I don't know, Oracle or SQL Server in the background. So you need to understand what are the caveats, potential caveats, what can be done and cannot be done in a certain way using this specific chosen platform. The same as for logical data models. There is a whole list of necessary steps to make your data model implementation a successful process. So let's focus on most important ones. First is choose the platform. This is a step that you cannot skip because this decision will shape all your future design principles. Translate logical entities into physical tables. The logical entity is just that, a logical entity, and it exists on a more abstract level. Since a real database doesn't support that level of abstraction, we need to translate that entity into a physical unit. This means we need to provide the information to the underlying platform on how the data should be stored. In simple words, define the data type of each entity attribute, be it a whole number, a decimal number, or plain text, for example. Additionally, each physical table should rely on keys to ensure data integrity. And it is your task during the physical data modeling process to set primary keys, foreign keys, and unique keys. Establishing relationships. Based on these columns that you identified as key columns, the next step is to, in this physical data modeling process, is to create relationships between tables. Again, apply normalization or denormalization, similar to what we talked about in logical data modeling phase. Again, this should be implemented in physical data modeling. Applying table constraints. There are dozens of constraints that you may apply to ensure data integrity. It's not only about the keys. Okay, keys are probably the most important ones, but there are also other constraints and other logical checks that you should apply on a database level. I'll give you a simple example. Let's imagine that your table contains a column that stores the data about students' grades in college. Can a student be graded with a grade 100 or 1000 or 1? Of course not. Maybe 1 in some systems, I don't know, but 1000 or 100 probably not. So there is a exhaustive list of possible grades, of possible values, let's say in the range of 5 to 10 or A to D in some other systems. So why not define this constraint on the column, thus preventing the insertion of the someone to enter the values that don't make sense, be it due an error or by leaving the end user possibility to enter whatever they want. Creating indexes and or partitions. Indexes and partitions are special physical data structures that reside within a table, and their main goal is to increase the efficiency of the data model. Keep in mind that both these features may significantly affect the performance of your data model, both for good and for bad. And I would say it is fair to say, especially for indexes, that implementing an efficient indexing strategy is mastery on its own. So you will find courses on the web, like 1-2 day courses just about indexing in databases. Extending with programmatic objects, almost every database management system will let you create various programmatic objects such as store procedures, functions, or triggers. Again, explaining each of these objects would require a lot of time, is out of the scope of this webinar, and they all serve different purposes and help you efficiently complete various tasks, but their implementation is considered de facto standard in almost every data platform solution, and it is hard to find any OLTP or OLAP system which doesn't rely on these objects. So if you want to explore more about that, I encourage you to go and check resources for understanding how to optimize database systems. Let me quickly check slides. I will share slides. It's not a problem at all. I'll share the slides after the session. Absolutely. Yeah. Okay. No exercises this time. Yeah. Okay. Yeah. Johnny is handling everything. Thank you. Okay. Let's proceed and talk a little bit about normalization. Normalization is one of the key concepts when you work with relational data. This concept basically means to organize the data in a certain way in a database. So normalization process implies creating a very specific data model. And since we probably all know that a data model consists of tables and relationships, normalization enables you to avoid data redundancy within the model, while at the same time setting consistent table dependencies through relationships. When you are building a data model, you will need to be aware that redundant data waste space and may cause maintenance problems. So during the normalization process, there are multiple different normal forms that your data is taking through this process. Achieving third normal form is considered necessary in most cases. And in this specific, in this session, we will talk about the third normal form, as it is used in most of data models. There are many, there are not many, but there are, I think, six normal forms. Maybe that's something that I forgot since my college days. But to be honest, I never used something that is higher than fourth normal form. So let's go and explain how to achieve the third normal form and how to eliminate the necessity to have the redundant data in your data model. The key feature of third normal form, and something that differentiates third normal form from other normal forms, is that it eliminates transitive dependency. That sounds scary, I would say, but let's go and explain what transitive dependency means. So let's say that we have a table like you see on your screen containing various data about the customer. And in this table, there is a dependency between the customer ID and state columns. But at the same time, state is dependent on the country, which means that customer ID is transitively dependent on country through an intermediate state column. To resolve this transitive dependency and achieve third normal form, I would split the customer table into two separate tables. One will contain the data about the customer, including state information, while the other table will store the data about the country. And these two tables can then be joined on the state column to retrieve the full customer data. This way, I'm eliminating data redundancy from the original table, and the overall idea is to enable insert, update, and delete operations to run much faster. I'll show you now how to normalize the data to a third normal form. So I have, let's say I have a wide flat table containing information about employees within the organization. As you may see, each row represents one employee, her or his name, job ID and job title, as well as the state code and state name of the employee. So this table is considered to be in first normal form. So let's pull our sleeves up and start with normalization process. I'll start by creating 3 separate tables out of this one. Employee, jobs, employee, job, and job. And this is how my tables look now. So let's focus on the employee table, where we have the location information for each employee. Remember, we've already learned that one of the requirements of the third normal form is to avoid transitive dependency. Currently in the employee table, the state is dependent on the state ID. Therefore, we need to move them to a separate table. So once I move them to a separate table, I leave just a state ID in the employee table and pull the information about the state name in the separate one. Then we achieve the third normal form. There are no transitive dependencies between the columns in this model. This was the concept of normalization. Denormalization represents the opposite concept, which we introduced so previously. So in online analytical processing systems, in OLAP systems, the emphasis is different compared to OLTP. In OLTP, we are mainly concerned about how to write the data into the database as fast and as efficient as we can. In OLAP, how can we read the data as fast and as efficient as we can? And by implementing denormalization, we are basically avoiding sometimes expensive joins between the tables, and we are creating redundant data in the table. Now, you're probably wondering, yeah, Nicola, isn't that bad to have redundant data in the table? Yeah, it usually depends. So let's see in which scenarios you might want to choose denormalization for your semantic models. We will talk about star schema, and why should you always strive to create a star schema for your business intelligence and Power BI semantic models. In this scenario, let's say that I have 3 normalized tables containing different attributes related to products. So I have dim product, I have dim product subcategory, and I have dim product category. Now let's say that this is so-called snowflake dimension, which we are going to talk about also later. Now imagine that most of analytical queries target the category of the product. So instead of performing 3 joins each and every time, so this is first join, this is second join, this is third join between the tables. So instead of performing 3 joins each and every time the query is run, we can denormalize the data model, put all the attributes within one table, and this table will be dim product. As you see, now I have redundant data in this table. So for product subcategory and product category, I have redundant data. But in the end, in some scenarios, this approach may bring some benefits. Instead of loading multiple tables in a data model, we will have only one, which should be more efficient in terms of performance because there are no relationships and no multiple joins between the tables. And also the overall data model complexity will be reduced. However, a word of warning, please don't jump to a quick conclusion that full denormalization should be your preferred way of data modeling in Power BI. Creating those giant flat tables containing tens of columns and millions of rows is usually the shortcut to self-destruction, how I like to call it, in terms of performance and flexibility. So denormalization makes sense in scenarios where you have these snowflake dimensions that need to be transformed into a regular star schema model. So let's jump into Power BI and start with the first demo. Where is my Power BI? Here it is. So let me drag it here. Okay. So I want to show you how to leverage Power Query within Power BI Desktop to denormalize the data. And let me first show you the data model that we have. So I'm using, let me just reduce a little bit. So I'm using this AdventureWorks sample database, which you can download for free and play on your own if you like. in AdventureWorks database, we have one central fact table called fact internet sales. We have, and I imported also a few other dimension tables like date, customer, and product. And you can see the example from previous example. I have dimension dim product, which is further normalized to include additional dimensions, dim product subcategory and dim product category. As we said, whenever the user needs to query the data about specific product category, this query will need to include join between three tables. So how can we eliminate this snowflake schema and basically move all the data into one table? I will click on transform data to open Power Query Editor. As I promised, everything we do today can be done from Power BI, so you don't need to open any SQL database, write any SQL code or similar. Everything can be done from Power Query. So in this case, I will go to my dim product table, and if I scroll all the way on the right, you'll see that this table is connected with dim product subcategory table. Whenever you have an active relationship between two tables, those two tables will be listed with all the available fields here on the right hand side of the selected table. In this case, I want to bring some information from dim product subcategory. So I'll simply apply join operation in Power Query. Join operation in Power Query is called merge queries. And if you go here at the top under combine and click on merge queries, then I'll find my dim product subcategory table, and I will perform the join on product subcategory key. So this is a common column between these two tables, and to perform the join operation, I'm choosing the common column between these two. Just in case that we don't lose certain records from dim product table, from our base table, because you see that there are certain records with null values, meaning there are no matching values in dim product subcategory. So in order to preserve those records in dim product table, I'll choose left outer join type. Left outer join, as it says here, it will take all the records from the first selected table. In this case, this is dim product, and return only matching values from the second table, which is in our case dim product subcategory. And when I click OK, I'm now able to expand this table, and I'll pick, let's say, English product subcategory name, and I will pick product category key, because that's the column that I'm going to use as a foreign key, within the relationship to bring the data from dim product category. Don't forget, we don't have product category key in dim product, so we need to go through the dim product subcategory to pick this value to be able also to join to dim product category. So I'll pick those two, and I will uncheck this option, use original column name as prefix. Once I click OK, these two columns are now already part of my dim product table. So the last step is to bring the data from dim product category, and I will again click on merge queries. And since I now have product category key in my dim product table, I can directly connect and perform join on dim product category. Product category key and product category key, those are common columns between these two. Again, I will choose left outer to preserve the structure and all the records from my dim product table. Once I click OK, similar to the previous case, I can pick all the values, all the records from dim product category table. In this case, let's say I need English product category name and nothing else. Once I click OK, now this English product category name is available directly from dim product. And since it's available from dim product table, what I can do, I can simply disable the loading of those two tables that were used for merging. So once I do that, they need to be here because they are used as references in my dim product table, but I don't need to load them into Power BI report because I already have all the necessary columns within the dim product table. And once I hit close and apply, these two tables here should disappear. And as you can see here, I have those columns, English product category name and English product subcategory name. Now they are part of the product table. We created redundant data, but we are now reducing the number of joins. So again, it's not that you should always, in each and every case, do that. It depends, but sometimes this solution of creating redundant data may optimize performance, but may also sometimes also increase the size of the data model. So always evaluate, but this is how you can achieve denormalization by using Power Query in Power BI. Okay. I see the question from Bogdan, when merging tables, is it better, memory efficient to perform this operation in SQL or using merge after we import tables? As a general answer, whatever you can do in SQL versus Power Query, do it in SQL. Yes, as Fred said, try to push all these transformations as upstream as possible. There is a famous Roche's maxim that says that perform all your transformations as upstream as possible, as downstream as necessary. This is absolutely true. Okay, so now let's move on to explain the concepts of OLTP and OLAP. So we already learned that entities represent objects of interest, and those objects are modeled in the form of tables. Column specifies various properties of this entity, such as product description or product category, or if you talk about the customers, customer names, customer address, phone number, I don't know. But some columns in those tables are different than others, and those columns are responsible for maintaining relationships within the data model. So let's examine a basic example of the relational data model. If you take a look at the customer ID column in the customer table, you can see that each row, each value of customer ID uniquely identifies. So each value in the customer ID column uniquely identifies row of the table. When a column or set of columns uniquely identifies a row in the table, this column is referred to as a primary key of the table. Every table should have a primary key. The same applies to product ID column inside the product table. Then we have order table. Our order table contains, as you see, contains both customer ID and product ID columns. The customer ID column refers to customer that placed the order, while the product ID column relates to product table, enabling us to find what product was purchased. Customer ID and product ID columns in order table are referred to as foreign keys. So they relate to primary key columns from other tables and are used to establish relationships between the tables in the data model. When we talk about relational databases, they're suitable for handling transaction processing in the most efficient way. Let's stop here for a second because we are talking about the online transactional processing. Let's understand what transaction means in terms of database workloads. Every proper transactional database must provide a so-called ACID set of rules to ensure that the database state remains consistent during the transaction processing. So let's examine what this ACID stands for. So A stands for atomicity. This means, or this concept should ensure that each transaction is considered as a single unit. And this unit can either be completely successful or completely unsuccessful. Simply said, if one of the statements within the transaction fails, the entire transaction fails. Then we have consistency. C stands for consistency. Imagine the transaction of transferring money from one account to the other. And in this transaction, when you add funds to one account, there must also exist a corresponding deduction from the other account. Consistency in this case means that transaction takes data from one valid state to another valid state. Then we have isolation. This concept ensures that the database will be in the same state when multiple transactions are being executed concurrently, the same as if they were executed in sequence. And finally, we have durability. Durability stands or means once transaction is committed to a database, it remains committed even if the whole system fails afterward. So we already mentioned that these systems are suitable for processing high volumes of data, high volumes of transactions. When I say high volumes, I mean millions of transactions per minute, hour, day, however you want, but this is a really huge number of transactions. The emphasis is on fast data processing. So tables are normalized, as we learned, to a third normal form to support quick and fast insert, update, and delete statements. These systems are convenient for running simple ad hoc queries for retrieving the data. And finally, here focus is on data integrity. That's one of the crucial tasks of OLTP systems. OLAP systems, before we come to explain this, a key difference between these two, this is of course simplified, there are many differences, but you can think from a high level about OLTP systems. Those are the systems that where you build your models to be optimized for data writing process, whereas OLAP systems are built, so models that we are building in OLAP systems should be suitable or should be optimized for data read operations. That's the main difference between these two. So OLAP systems are designed to enable users to understand the big picture of the data stored in the database. So that means, unlike in OLTP, where the focus is on a single transaction, here the focus moves to aggregated data. So using the OLAP system, we can extract information from a large database and perform analysis to support business decision-making process. So the main purpose of OLAP systems is to generate insights from transactional data. So those insights can enable business users to understand, I don't know, sales trends, customer retention and satisfaction, finding potential bottlenecks and improving business processes, and many, many more. Here are the key differences between OLTP and OLAP systems. So as I said, I will share this slide, so I won't go through each and every bullet point. More or less, we covered all of these differences in previous slides. So those are the main, or let's say, key points for both OLTP and OLAP systems. Okay. Let's move on to dimensional modeling. So if you find yourself surrounded by experienced data modelers, you'll probably hear them talking about stars and snowflakes. Don't worry, they didn't become astrologists or nature researchers all of a sudden. Star and snowflake schema that we're going to talk about a lot in the remaining part of this webinar, those are probably the most influential concepts in the world of dimensional modeling. So let's first try to explain what dimensional modeling is. Approximately 30 years ago, or exactly 30 years ago, there was a guy called Ralph Kimball, and he came up with, back then, a revolutionary approach of how to model the data to support efficient business reporting. And he's still considered, let's say, a godfather of dimensional modeling. There was a completely new approach. Now, if I try to explain to people what are the different concepts and the key characteristics of dimensional modeling, I like to introduce this small, it's not a game, but let's say, imagine that you have a big treasure map with different rooms inside. Think of it as your magical map. So what we have here, we have a toy room, which shows, for example, what kind of toys you have. It also contains the list of all the toy names, toy colors, toy types, and so on. So it helps you understand, or it provides the information and help you understand your toy collection. Think of it as a product dimension. Okay. Then we have a friend room, which shows who your friends are, also contains the list of their names and where they live, and it will help you to remember who of your friends plays with which toys. Think of friend room as a customer dimension. Then we have a calendar room, which shows when you got your toys, also has different information about months, about seasons, and so on, and it helps you to track when certain things happened. This is a calendar dimension or date dimension. We have a playhouse room, which shows where you got your toys. It also contains the list of different toy stores where you like to go, and also helps you to remember various shopping places. Think of this as a store dimension. And then we have in the center, we have our central room. This is our main treasure room, which contains special numbers like how many toys we collected, and also connects to all the other special rooms. So the real magic happens when these rooms are connected. So when you want to know something, how many blue marbles or red cars I got this summer, you can easily walk between these rooms and find that answer very quickly. It's like having a super organized treasure map where everything has its perfect place and you can find any information very, very fast. Now, talking about additional concepts that exist in dimensional modeling. The first concept is surrogate key. Again, let's try to explain this in a more simplified way before we move to the one for the adults. So the concept of surrogate key means, let's say you have a big toy box with lots and lots of toys. Sometimes toys look very similar. For example, you can have two identical teddy bears. So you put a special sticker on each toy with a unique number. And this sticker, this is your surrogate key. So it's a special code that makes each toy completely unique, even if they look exactly the same. Okay? And then we have another key, which is called alternate key. And this is the original name tag. This is the original tag that came with a toy, like its name or description and so on. For teddy bear, think of, for example, brown soft teddy. And this is something that we as humans usually use to identify when we talk about something. However, this might change, or it might be similar to other items, or what's even worse, can be sometimes same for multiple toys. So if I show you something like this, I have two brown soft teddy bears. If we talk about the alternate key, they are both brown soft teddy bears. But from the perspective of the database and from machine readable and uniquely identifiable records, we will put this secret code sticker to each of these teddy bears. One will be toy 001, another one will be toy 002. So this is the difference between surrogate key and alternate key in dimensional models. Now moving to the part that is for adults, to put all of this into, let's say, back into real world. So we have, or Ralph Kimball says that every table in dimensional model should be labeled either as a fact table or dimension table. So fact tables helps us to store the data or information about the events, various events that happen. They contain numeric and additive data, and usually answers this question, how much? So how much did we sell? How much money did we make? How many customers did we lose, and so on. And then we have dimension tables, which provide context for this analysis. And when I say context, they contain descriptive data. So think of them as lookup tables. When you need to find a specific descriptive information about specific event, then you go to the dimension table to pull this data out of there. They usually answer the question starting with W. Who bought something? When did they bought? Where did they buy? And so on and so on. So think of it as think of those questions. Dimension tables should answer those questions. This is an example of a fact table that contains foreign keys to dimension tables. So we have 3 foreign keys, and we have numeric value or measurement, which is in this case sales amount. Usually in real life, most of the fact tables, or let's say they should be modeled in that way, that they consist only of foreign keys to dimension tables and measurements that you need to aggregate. So no descriptive data should be kept in fact tables. There are some exceptions here and there, but in 99% of cases, let's say, you should model your fact tables to contain only foreign keys to dimension tables and measurements that you want to aggregate. This is a typical dimension table. Dimension table contains a primary key that uniquely identifies each record within the table and different attributes. Now, these attributes may vary from having one attribute for the specific object to having hundreds of different attributes for a specific object. It depends how your business and what are the attributes that are relevant for business users in their analysis of the data that is stored in the database. So technically, or let's say conceptually, dimension table consists of a primary key and various attributes. Another important concept, this one is probably one of the top 3 concepts in entire dimensional modeling, is the concept of granularity. Granularity stands for the level of detail in the data set that you have. That means what is the lowest level of the detail that is acceptable to the business user for data analysis. And let me give you a very basic example so you will understand why granularity matters. Let's say that you store the data on a level that is specific date, so on a day level. And let's say that your users need to analyze data for every single hour within that day. If you don't have data on a level of detail that is lower than day, they're not able to perform that kind of analysis. So as a rule of thumb, you should always keep the lowest possible level of detail when you store the data in the dimensional model, because you never know what is going to happen in the future. If you build your model and your tables on a higher level of detail, then this means if someone in 6 months want to analyze more detailed data, they will not be able to do that. It's better to start with the lowest possible level you have. So let's say individual transaction. And then it's easy to aggregate the data afterwards in Power BI or any other tool of choice. It's easier to aggregate the data later. Similarly, if you store the data on a manufacturer level and your users want to analyze data on a level that is individual product within the manufacturer, they will not be able to do that if you didn't set the granularity to store the detail about specific product. Okay, implementing a star schema is basically implementing these fact and dimension tables that we previously discussed. So a star schema consists of a fact table that is usually placed in the middle or in the center of the data model, and it is surrounded by 1, 2, 3, 5 dimension tables. Why it is called star schema? If you take a look at this illustration, you will probably conclude on your own. So this is the basic concept about star schema. Again, talking about surrogate key and alternate keys. When you are implementing star schema, your tables should contain should rely on surrogate keys. If you're wondering why star schema, why this should be let's say a preferred way, and you will understand that also later during the demo, with star schema it really allows easy navigation through the semantic model. It allows easier and faster model modifications, reduces complexity of the model. It provides a consistent analysis, and Power BI engine, if we talk specifically about Power BI, is optimized for star schema models. If you don't trust me, I don't mind. That's totally fine. I will share the link later, or maybe Johnny or Pragati, if you have somewhere close to you, the link to Microsoft's official documentation, Star Schema Guidance, where Microsoft explicitly says that whenever possible, you should structure your models or design your models as star schema. And that's why we say that star schema should be a default choice when building Power BI models. There are some additional concepts that I want to mention here, because in real life, let's be honest, in real life, it's very hard to achieve the perfect star schema. It's possible in demos, it's possible in some real life use cases, but generally speaking, in real life, we will have different variations of dimensional models that include star schema, but also some other hybrid concepts. Yeah, thanks, Johnny. Thanks. So first concept is snowflake schema. We already scratched the surface in the previous case when I talked about denormalization. This example with dim product subcategory, and dim product category, this is a good example for snowflake dimension, dimension that is additionally normalized, further normalized. It allows for setting more granular dimensions. So in case that that works for you, this is also a valid approach. So let's see how to implement a star schema with Power BI. Let me just close this one and open a new file. Okay, let me show you the model, or if we can call it model. It's a one flat table from AdventureWorks again, and you see that this table contains everything. When I say everything, I mean it contains descriptive data, it contains measurable data, so numeric values like sales amount, unit price, tax amount, but it also contains the details about the customer, like first name, last name, birth date, email, also data about the products, like product name, color, size, and so on and so on. So let's see how we can leverage Power Query to build from this one flat table to build a proper star schema. So I'll click on transform data and open Power Query. Now let's start working, and I'll first create a dimension table for our customers. Let's say I will start with customers. So I will right click on the existing query and duplicate it. Let's call this one customer. So what are the columns that are relevant to our customers? Let's see. It starts from here: first name, last name, birth date, email, education, and address. So I'll go to choose columns, and then I'll select only those columns that are relevant for the customer. Okay, and let's mark now all these columns. Don't forget, in dimension tables, each row should be uniquely identified. So we should not have duplicates among our customers. Each customer should be uniquely identifiable. In this case, as you can see, I have this John Young repeating, I don't know how many times, 8 times. So I marked all the columns, right click, and then choose to remove duplicates. Okay. Now we have all of our descriptive attributes here in this table. We got rid of duplicates. The next step is to create a surrogate key. In Power Query, you create surrogate key by using a special transformation called index column. So if I go here at the top to add column and then choose index column to start from 1, this is a surrogate key, just a meaningless numeric value that sequentially goes increases by 1, and now I can uniquely identify each of my customers. So let's call this column customer key, for example, and I will simply drag it at the beginning. Usually this column comes at the very beginning of the table. Okay, that was our customer dimension. Now let's create our product dimension. Very similar steps. I will again duplicate my original query and call this one product. Okay, let's go and check which columns are relevant for product. So I'll deselect everything. It starts here: product name, product color, product size, model name, product subcategory, and product category. Okay, I removed everything. Again, let's select all the columns and remove duplicates. And finally, let's add our surrogate key that starts from 1. I'll call this one product key. Okay, I'll drag it at the beginning. And now I have my product dimension. If I go to the original query, and if you take a look now, we are probably good to go, but we are lacking, I would say, the most important table of every dimensional model, and this is a date table or calendar table. So every proper semantic model should contain a dedicated calendar or date table, call it however you want, but don't rely on features like auto date time in Power BI for different reasons. So always create a proper date dimension in your data model. In this case, I have just one table that is related to dates and time reference to the transaction. There are multiple ways you can create date dimensions. The ideal way would be if you have it already defined on your data source level. Let's say you are connecting to the organizational data warehouse. Chances are that this data warehouse already contains a well-designed date dimension with all the attributes that are needed for your business, and you can simply connect and use that one. In this case, unfortunately, I don't have it, so I can either choose to create it in Power Query, or I can choose to create it in DAX. Those are both valid approaches. In this case, I will use Power Query. Why is this important? Because let's say that our company is closed during weekends, so you will have gaps in this order date value. And in order to be able to apply time intelligence calculations in DAX later in your Power BI report, your date table must contain a column, special column, date column, that contains continuous values. So in case there are any gaps, time intelligence functions will not work. So in this example, I'm not sure if in AdventureWorks there are some gaps or not, but I don't want to risk. So I will create a proper date dimension and then simply connect it to and build a star schema, build it as a part of my star schema. So you can do it in multiple different ways in Power Query as well. There are many ready-made scripts on the web that you can grab and simply copy paste and put here to have a proper date dimension. So there is really no excuse for being lazy. And what I will do in this case, I will create with parameters. So I'll create 2 parameters for my starting date and ending date. So this one I'll call start date, and it will be of data type, and it will start on 1st of January. I'm not sure when this data starts. Let me first check that. So let me first see. So I will load everything and then sort in ascending order. It starts from 1st of January 2018, and the last one, okay, it's not here, probably I think 2021. So let's be safe, and I'll create a parameter that starts on 1st of January. 1st of January, this is date type, and it will be 1st of January 2018, and another one which will be end date, and again date type, and this one will be 31st of December 2022, just to be sure. Okay, doesn't matter, this can be changed later. Okay, so now I have my parameters to help me control which is the date range that I want in my date dimension. I'll now right click here, choose new query and then blank query. Again, I'm doing this from scratch. You can simply copy and paste the definition for the entire date dimension somewhere from web. So I will now, because I have a list, basically what I need to do is to transform this list to generate the entire list with all the values in between those two dates. So I will list dot, did I miss something? List dot dates, and then let me see. Okay. Okay, I already pasted here. So let me just delete this. I already pasted. Let me see if this is going to work. Let's try again. If I do it like this, see, okay. Let's start again because something is, okay, I know what's the problem. Those numbers are problem. Okay, this should work now. Yeah. So now I have a list of all the values between 1st of January 2018 and 31st of December 2022. And finally, because this is list and I need a table, I'll simply click on to table, this transformation, to transform and convert my list into a regular table. Few more things that we need to implement here. First is to change this data type of the column from any to date, and I'll call this one date. Now also let's rename this to date, and based on this one single column I can generate additional columns that are related to date. For example, I can extract the year, then I can, for example, extract start of year, I can extract, I don't know, month. So let's pull some of those. Name of month, and then, for example, day, and so it's as easy as clicking. So yeah, really no need to reinvent the wheel. Okay, so now I have our my date dimension that I'll use in the star schema. Finally, let's go to our original query and let's bring those values from dimension tables. Let's bring our our primary keys from dimension tables and use them as foreign keys in our main fact table. So how do we uniquely identify each product? I will simply go here and click on merge queries. So I need to bring the information from the product, customer, and date dimension. So I'll click on merge queries, and this is my product table. In this case, uniquely identified by product name, product color, product size, model name, product category, product subcategory, just to be sure that we are not missing anything. Once I create, please pay attention that when you are doing merge operation, the order of columns is important. So it can mess up if you switch different columns in the order of columns. And I'll do left outer join. You see that all selection is all the rows are matching the selection. I click OK, and now when I expand this table, I'll pick from it only product key because that's the one I'm going to use to establish relationship. So I have product key for each of my products. Since I have this, I don't need those descriptive attributes anymore. So I will simply go and remove those columns from my fact table because they are now part of dimension table. When I need this information, I will simply pull it from the related product table. Let's do the same thing for customers. So I will again go and choose this one and merge queries, going to pick up my customer table. And what we have here, we have first name, last name, birth date, email, education, address, and now product key, we don't need it. And here I have first name, last name, birth date, just in case that you have two customers In theory, you can have two customers with same first name, last name, birth date, email, education, and address. It can happen, although this is not high probability, but it can happen. That's why it is important to do it this way. Okay, I'll again checking the selection match. That's okay. And expanding the table like I did in the previous case, I'll grab customer key from my dimension table, click OK, and now I can remove all the descriptive attributes for the customer. So I don't need those. Remove those columns. Okay, so now what we have in our fact table, this is how fact table should look like. We have foreign keys to our three-dimension tables, order date, product key, and customer key. And we have numeric values. I'll keep sales order number, sales order line. Those are unique identifiers for every single transaction. We don't need to create a surrogate key for date table because each date is unique. There cannot be two January 1st of 2018. So I'm sure that here I have unique values for dates. So I will simply create a relationship between those two. Once I hit close and apply, Power BI will load the data. And now if I go to my model view, let's see what we have here. This one is not a flat anymore, so I will just call it sales. And we have now an opportunity to see the star schema model built in Power Query. The only piece that is currently missing is a relationship between the date dimension and sales table. So I'll simply create a relationship between the date and order date column from sales table, click save, and I have nicely built, nicely looking star schema model that I can now use in Power BI. Okay, so let me just take a quick look. I see everything works smoothly. Thanks, Johnny and Pragati. Yeah, Tom, thanks for joining. No worries. Okay, so that was an example of how to create a star schema with Power Query in Power BI. Let's move on. We have few more things to cover. Talking about the extended concepts for dimension tables, there are two additional concepts that I want to introduce. The first one is slowly changing dimension. This one is for all of you who ever worked or read something about dimensional models. You are probably familiar with that concept. So slowly changing dimension. The emphasis is not on the speed. The emphasis is on the fact that the data can be changing in your dimension tables. So slowly changing dimension means how do you handle changes to the attributes in dimension tables. And sooner or later, probably you will face the requirement to capture those changes. And now it's up to you to decide how you want to track those changes. There are similar to normalization forms. There are also 6 different types of slowly changing dimensions, although 0, 1, and 2 are most commonly used. So 0 means there are no changes to dimension, so data will not be updated anytime in that dimension. For example, if you use a calendar table, 1st of January 2018, or I don't know, today is 27th of March 2025, it will always be 27th of March 2025. It cannot change, this attribute cannot change the value. Then we have slowly changing dimension type 1, which means you simply update the existing record with a new value. I'll give you an example. I used to live in Belgrade until 2016. Then I moved to Salzburg. Now I live in Salzburg, and let's say I moved to Barcelona in 2025, so this year. Hopefully, we'll see. Now, if someone wants to analyze the data about me as a customer, what is my current location? My current location is Salzburg. Once I move to Barcelona, they will simply overwrite my location from Salzburg to Barcelona. Or when I moved from Belgrade to Salzburg in 2016, they simply overwritten my location from Belgrade to Salzburg. Now, what happens if someone wants to analyze my spending habits in 2015? And let's say they want to analyze spending habits by location. So if they go and put the date or year equals 2015, I will appear as someone who lives in Salzburg, even though it was not the case in 2015. So it will produce, I wouldn't say incorrect data, but maybe unexpected data or unexpected information to the user, because in 2015, I used to live in Belgrade, not in Salzburg. But when you simply overwrite the value, then there is no this history tracking for attribute change. And that's why in most of the implementations of dimensional models, slowly changing dimension type 2 is most commonly used one. This one stores the information about all the changes that happen to the specific attribute by adding a new row for the specific record. So in my example, again, once I moved, so I was stored as Nikola, who lives in Belgrade from my birth in 1979 until 2016. Then when I moved to Salzburg, there is a new record in a table, in the dimension table. Again, it's Nikola, it's me with the same customer key. I have another record in that table, but in this case, it says from 2016 until some day in the future, or if it's unknown, sometimes it's null, whatever, I live in Salzburg. Once I move to Barcelona in 2025, there will be a third record for me, which says from 2025 up until some date in the future, Nicola lives in Barcelona. So when the user needs to analyze the data for 2015, I will appear in Belgrade, because there will be a record in the table that specifically says that I used to live in Belgrade in that year. If they want to analyze data from 2020, I will appear in Salzburg. So that's why this concept of slowly changing dimension type 2 is most commonly used in dimensional modeling implementations. There are different types of changes that can occur for attributes. Customer address is one of the examples that I also did on my case. Product price, so whatever change to the attribute happens, you need to capture this change and store it as a slowly changing dimension. There are two more types of dimensions. The first one is conformed dimension. Conformed dimension means when one dimension is shared across multiple fact tables in your semantic model, this dimension is then called conformed dimension. There is nothing specific about this dimension, like slowly changing, where you add new records and so on. So there is nothing specific, but I just want you to be aware that you can use one dimension table to filter the data from multiple fact tables. And in those cases, we are referring to those dimension tables as conformed dimensions. And we have another interesting concept, which is called role-playing dimension. This one requires a little more explanation and also a short demo, so I will show you that as well. So role-playing dimension means, like, simply said, it's the situation when you use one same dimension for creating multiple relationships to your fact table. Typical usage of role-playing dimensions is with date dimension, when you have a fact table that contains multiple date fields. For example, in the sales table, you have columns like order date, due date, and ship date, which don't need to be identical. And in most cases, they are not identical. So in those cases, you might want, based on user requirements, you might want to establish multiple relationships to the same table. And although the role-playing dimension concept is not exclusively related to Power BI, there are certain nuances for its implementation in Power BI models. So concept of role-playing dimension exists outside of Power BI, but inside of Power BI, because of some specific ways of how what Power BI allows you to do in those scenarios, there are certain things to keep in mind. One of those specific things is a special DAX function called use relationship that allows you to activate inactive relationship. I will show you soon in a demo. So let's do a demo. Let me see. Just a second. I'll close the existing one, or let's leave it here. I will just open another file that I prepare for role-playing dimensions. Yeah, I see point from Fred. Yes, it's not sorted. It's not marked as date table. This is just for the sake of saving some time, but you're totally right. Yeah, you're totally right. This should be done. This should be done. Those are great points. Yeah. Yeah, Milos also, yeah. People changing teams or departments within a company, any change that happens to the attribute in a dimension should be captured so you can do point in time analysis, go back and forth and analyze this data. Okay, so we are now in role-playing dimensions, and what I wanted to show you is, again, we are using this AdventureWorks sample database. I have a very simple model, consists of just 4 tables: fact internet sales, dim customer, dim product, and dim date. As you may see, currently there is no relationship between the dim date and fact internet sales. The reason is very simple. I have multiple date columns in fact internet sales table. So I have order date, I have due date, and I have somewhere here, I have also ship date. So Power BI doesn't have an idea which one I want to use for establishing relationships. It can be any of these 3. Let's say that my default relationship will be on the order date. Most of my customers are interested to see how our numbers are developing over time based on the order date. So I'll create manually this relationship. I will connect full date alternate key with order date column and click on save. Okay, now if I, for example, go to the report and let's build something very simple, like I'll put a table visual and I'll put, for example, calendar year, and let's create a very simple measure for sales amount, which will be a simple sum of the sales amount. Nothing fancy. And sales amount. Let's say that. Okay, let's leave it like this. Now, what happens if our users also need to analyze the data per due date or per ship date? So to compare, for example, how those 2 sales amounts progressed over time, not only per order date. Currently, this is not possible. And there are 2, or let's say at least 2 approaches how to solve this. The first approach is to implement role-playing dimension by creating a duplicate of the existing date dimension and then connecting this duplicated table to the ship date or due date. So let's do that first. So I'll simply go here and I'll create a duplicate of my dim date table. I will just call it, for the sake of clarity, dim date ship. So I know that it refers to a ship date, or it will refer to a ship date. I'll hit close and apply. And once it's loaded, what I'm going to do, I will find this full date alternate key. That's a key column in my dim date table, and connect it here to ship date. So that's approach number 1, creating multiple copies of the same dimension table, and then each copy of this dimension table plays a different role. This one plays role of the ship date table. This one plays the role of the order date table. I could have created a third one, which would play the role for due date table, but let's keep this part because it's the same as the previous one. And now if I go and copy paste this visual, and instead of using calendar year from my dim date table, I will go to dim date ship and put that one here. Now you see the numbers are different because in this case, the data is filtered based on the ship date, not the order date. Now the next requirement, your users are partially happy, but they also want to analyze those numbers within the same visual. How can they do this? Not with this approach, because in this case you will have just one unique axis for each of those date tables. So for this to work and to enable your users to compare numbers per ship date and order date within the same visual, you must go with another approach, which is using one same table, establishing multiple relationships, and then with DAX controlling which relationship is active. So let me quickly show you how it's done. So I'll get rid of this one, dim date ship. I will delete it from model. So I still have just one date dimension, the one where I establish relationship between the order date and date key from date dimension. Now what I'm going to do, I'm going to create another relationship to a ship date and save it. Now, if you take a thorough look here, you will see that one of those lines is dashed. This is because Power BI allows you to have only one active relationship at a time. So only one relationship can be active at a time. You can't have multiple active relationships at the same moment. Okay? So this one, the order date, will be our default one. And the one on the ship date is currently inactive, but we will leverage DAX to activate it just for the sake of the specific calculation. So once I go back to my report, let's remove this. Once I go back to my report, I have this sales amount calculation, and this one by default will use the filter that exists through the relationship, through the active relationship. Our default active relationship is in order or order date, so I don't need to touch this. I don't need to change this. But in order to be able to activate my inactive relationship, I need DAX. So I will create a new measure. Let's call this one sales amount ship. And it equals, because we are basically modifying the default filter context, we need calculate. So I'll write my statement starting with calculate. First argument is the expression. So we want to calculate the sales amount. And now we need to provide the context in which we want to evaluate this expression for sales amount. In our case, we want to activate the inactive relationship. And this is done by using this use relationship special function in DAX. So use relationship requires two arguments, and those two arguments are the columns that are building blocks that are part of this inactive relationship. So in our case, this is full date alternate key from dim date and ship date from fact internet sales. So just to be clear, to be able to use relationship, there must be a physical relationship between the tables. So if you don't create a relationship, even though it's dashed line, even though it's inactive, if it doesn't exist, you can't use relationship. So use relationship relies on the physical relationship between two tables. And once I click OK and drag this measure here, now you see that we can compare these values within the same visual. Table visual, maybe it's not the best approach. On the line visual, you can compare how lines move differently between the order date and ship date. But this is the way to solve this issue. I also suggest, whenever possible, I know it requires maybe some effort from your side to create those DAX calculations, but in the end, your model is less complex than when you create multiple copies of the same table. And I think it's also easier for understanding. It's more, let's say, intuitive when you do it this way. So that was about Okay, let me see. Yeah, okay. Lively conversation, just keep it up. Nice. So let's talk about relationships. We are slowly moving towards the end. Relationships are one of the key concepts in data modeling. And unlike in traditional relational database scenarios where when we cared only about the relationship cardinality, in Power BI semantic models, relationships also serve as filters between the tables when you are running DEX calculations, like you saw in the previous example with role-playing dimensions. So let's first examine the concept of cardinality in relationships. There are four possible options to choose from, even though one is just a variation depending on the filter direction. We have one-to-many and many-to-one, which is basically the same, one-to-one and many-to-many. The one side of the relationship means that the column contains unique values, whereas the many side means that the column may contain duplicate values. So one-to-many and many-to-one are essentially the same. The only difference is where the relationship starts from or in which direction filter is going. I'll give you a very simple example. Let's say that we have two tables in our model, product and sales. There is a product key column in both tables, and we created a relationship between two tables on that column, common column. However, because the product key in product table contains only unique values, if we define a relationship that goes from this column, so the filter propagates from dimension table to the fact table, we are talking about one-to-many relationship. If we change the way of filter, then it will be many-to-one. But from the cardinality perspective, it's the same. Then we have a many-to-many relationship. I've intentionally skipped one-to-one. I don't want to talk about this because this is really suboptimal model design and really, yeah, I don't see any use cases or maybe very, very rare use cases for one-to-one. But many-to-many are also considered as exceptions, even though they exist in lot of Power BI semantic models. Uh, if you have fact tables with different grain, with different granularity, or if you are connecting many-to-many dimensions, many-to-many relationships are considered as a way to go. A good example of having many-to-many dimensions is customer and account. So this means that one customer can have multiple accounts. Also, one account can be shared by multiple customers. And in this scenario, a recommended practice is to create a so-called bridge table, which stores unique combination of each customer and account. And then we create two one-to-many relationships between our dimension tables and bridge table. So we resolve the challenge of having many-to-many relationship in our model. Another important concept is the filter direction. There are two possible options: single direction, which is a recommended practice, and both directions or bidirectional filter. This option has its use cases. I wouldn't say don't use it, never ever, but should be implemented with care, with special care, let's say, because it can produce inaccurate results and it can also affect performance depending on other things that you have in your model, but it can affect both performance and data accuracy. So just be careful when you are implementing bidirectional filters. The arrow on the relationship reveals the filter direction. In this case, we are talking about a single filter direction going from product category table, then to the product table, and then all the way to the sales table. This means we can filter values in both product and sales tables by selecting a value in the product category table, but not the other way around. So I cannot select something in my fact table and expect that this selection will propagate and filter the data from the dimension table, because the arrows, their direction says that they are not going from my fact table back to dimension table. If I enable bidirectional filtering, then I can do that. Then this selection in the fact table will also propagate in another direction, and I can filter the data in the dimension table. Now, do you want to do that? Probably not, but I don't know. Sometimes maybe use cases for bidirectional filters, as I said. What I wanted to stress here is that in most cases, people are going the easy path. Like it's easier to enable bidirectional filter and give this model to the user and it will work until it stops working. So I would say be careful when enabling bidirectional filters. And there is also a special function in DEX like we had for activating inactive relationships. There is also a function called cross filter that you can use to enable bidirectional filters just for the specific calculation. So instead of opening a relationship in both directions by default for everything, you can, for those scenarios where you need somehow to propagate the filter in another direction, you can use cross filter function and then open the relationship in both directions just for the sake of this specific calculation. Okay, few more things. Talking about building proper models in Power BI when we talk about large amounts of data. So it's easy, and I really think that Power BI is a kitchen sink when you work with less than, let's say, 1,000,000 rows. So it doesn't matter what you build. And even if you don't implement star schema, if you don't follow all these best practices, you can live with that. I'm not saying you should do that. You don't need to care if your models are small, not at all. But you will not notice a significant performance decrease, or you will not pay the penalty when your data amounts of data are smaller. Once the data starts to grow, then it's super important to understand how Power BI stores the data and what are the best practices when you need to deal with these larger amounts of data. There are two types of tables. Generally speaking, there are two types of tables. Yeah, thanks, Johnny. Thank you. Thanks for helping. Really appreciate it. There are two types of tables. We have a tall table, so-called tall table, which has many rows and not so many columns. A good example is the fact table. Usually fact table doesn't contain 50, 60, 100 columns. It's usually a narrow table, but it has a lot of rows because every single transaction is stored. So this is a tall table. Then we have a wide table that has many columns and not so many rows. Dimension tables are usually example of these wide tables. Sometimes, of course, there are exceptions. You will have a dimension table with millions of records. It happens, but usually dimension tables don't go so far in terms of number of records. So we commonly talk about wide tables as dimension tables. But if you use both tall and wide tables, meaning if you put everything in a single table, and this table contains tens and tens of columns and millions of rows, then it's a problem. It's a problem. So you should avoid this scenario where you have both tall and wide table in Power BI. One last topic is about composite models. And with composite models, yeah, first, let's say that in dark ages of Power BI, although I know that today it's hard to believe that Power BI had a dark age period, but that's true. So if you wanted to use direct query, for example, as a source for your report, once you've chosen direct query for a certain data source, like SQL Server, for example, the possibility to extend on this was gone. To put it simply, you couldn't combine a direct query query over one data source like SQL Server with direct query over another data source. Think of Oracle database or MySQL database, whatever. Let alone combine direct query with import mode. This was not possible. But as I said, since a few years ago, now it's already here. You can create a data model in Power BI that consists of, let's say, data coming from the Excel file stored on your local machine, then imported data from the SQL Server database, direct query that retrieves data from another table from another SQL Server database, and direct query that retrieves the data from, let's say, Oracle database. Keep in mind that when you create composite model, all imported data sources. So it doesn't matter if you connect from Power BI to SharePoint list, Excel file, and SQL Server table. Once you create an import mode semantic model from these tables are considered as one source group, one data source. And then you can bring additional tables that are in different storage mode. In this example here, I have tables coming from Oracle database and from different SQL Server database. Now, if you ask yourself why some arrows are dashed and others are not, that's a good question. These arrows represent relationships between tables in different storage environments. So tabular model supports, in Power BI, tabular model supports two types of relationships, regular and limited relationships. Sometimes you will hear people referring to them as strong and weak relationships. Explaining now the behavior of all of these, of both, especially about limited relationships, is out of the scope, unfortunately. But as their name suggests, because they are limited, there are many limitations, many potential caveats that you should be aware of. In these scenarios, to overcome this limitation of limited relationship, there is an option to choose a third mode in Power BI, which is called dual storage mode. So just to illustrate what I'm talking about, if I open another Power BI desktop file, okay, and in the model view, I have 4 tables that are in direct query storage mode. You can tell that by looking at the header of the table. This solid blue line means that the table is in direct query storage mode. So I have those 4 in direct query mode, and I have, let's say that I store the data about the budget on SharePoint list. So I imported this data into Power BI. This one is using import mode. And now if I create a relationship between my dim date table and date column from budget table, please notice the difference here and here with this one. So whenever you have this like small break of the relationship, this is a limited relationship. It comes with many limitations. And to resolve this, what you should do, simply the table that connects to the tables from different source groups. In this case, we are connecting to import table and to direct query table. Expand advanced and choose dual storage mode. With dual storage mode, what happens is that Power BI basically keeps 2 copies of the same table. One is in import mode, another one is in direct query mode. So there are 2 copies. And now you see that this relationship is also considered a regular relationship. There are no breaks in the relationship line. And now during the query time, if the data is needed from the table in import mode, this dim date will behave as import mode table. If the data is needed from any of those direct query tables, dim date will behave as direct query table. So this is how in composite models you should set tables that connect to other tables in the model which are in different storage modes or belong to different storage groups. Okay, one last thing that I wanted to show you before we conclude is how to handle multiple fact tables in your semantic model. So I'll close this one, we don't need it. And let me open this star schema. Okay, so we built star schema. Let's follow Laurent's suggestion and mark this as a date table. You're totally right. You're totally right. It was just for the time saving purpose. I'm not lazy. Okay, so let's say that now the requirement is that we also want to analyze the budget data. So how do we handle this requirement? And let me first show you how this budget data looks like. So currently we have this data stored on a day level, right? And in product dimension, we have a separate record for every single product. So a particular product is the lowest level of detail in our product dimension. Now what happens if I go to new query and I store this budget data in Excel file? Let's connect to this table. As you can see, there is no product here. We don't plan our budgets on the product level. We don't go so low in this level of detail, but we are setting our budgets on category, subcategory, and date level. So in this case, the combination of category and subcategory is the lowest level of detail, or because there are multiple subcategories that belong to one category, we can say that the lowest level of detail is the product subcategory. As you can see in accessories, we have, I don't know, 10 different subcategories and so on and so on. Now, if I go back and hit close and apply, let's just give it a proper name. This will be budget. And if I try to connect date, my current date table, to budget date table, click save. This works like a charm because we have the same level of detail. And this is a good example of the conformed dimension we previously mentioned. So when one dimension table is shared across multiple fact tables, we consider this dimension table as conformed dimension. Date is conformed dimension. Now what happens if I try to take product subcategory from the product table and connect it here to product subcategory? Power BI complains that there will be many-to-many relationship because we don't have unique values on both sides of the relationship. We have duplicates on both sides of the relationships. And to solve this, again, I'll go back to Power Query Editor. I will use my product dimension that I've already created and prepare it in that way. So I will create another table that will follow the same granularity of my budget table. So I will duplicate my product dimension, and let's call this one products budget, so we know what we are working on. And in this case, we just need product subcategory and product category. We don't care about other columns. So I'll simply mark these two and choose to remove other columns. Okay, so now the next step is, again, we need uniqueness of the data here. So I'll mark those two and click remove duplicates. And now I have unique combinations of both product category and product subcategory. Okay, so we remove duplicates, and for example, I can also sort the data here in ascending order per product category. Next thing is we want to create a surrogate key that is going to be used instead of these textual values. So again, I will choose these two and go to add column, index column, and then I'll call this one budget category key, for example. Okay, and let's move it here. Now we have also our surrogate key. Okay, we now move on to our budget table. We need to somehow combine this data into our budget table. So I'm in the budget table. I will go to merge the query. So I need to pick up this surrogate key, which is a primary key in my product's budget dimension. I will use this as a foreign key in my budget fact table. So I'll merge queries and connect to my products budget based on, please be aware, so subcategory is the first one and category is the second one. It's different in these two tables. So if you swap the order, it will return nulls. In this case, should work. So I'll expand it and pick my budget category key. Yeah, looks good. Let's put it here. And now I don't need category and subcategory anymore because we have this information in our product's budget dimension. So this budget is just a fact table, nothing else, but on a different level of granularity than our current product dimension. That's why we had to adjust this granularity to be able to perform this type of join. So I'll remove these columns. Now I have these remaining 3 columns, and finally I'll hit close and apply. And as you can see, now my tables are connected through the budget category key, and from this moment I can use also this part of the model for performing data analysis. So essentially what we have here, we have 2 star schemas. This is the 1 star schema with sales, date, customer, and product, and we have another star schema which is budget, date, and product budget. To be able to visualize that, for example, I can take something like this. So I will drag my sales table and then add related tables. You see, this is our star schema number 1, and here I will drag my budget and add related tables. This is our second star schema. So this is how you can handle multiple fact tables with different level of details. We did a composite model. Okay, few more things before we say goodbye. Where to go from? This was just a basic introduction to data modeling, of course, but I have some great resources for you. Starting from the left, the Data Warehouse Toolkit, the Bible of dimensional modeling. So if you look for the resource for reading, this was the creator of dimensional modeling concept, Ralph Kimball, and his group. So Kimball and Margie Ross, they wrote this book, which is absolutely relevant nowadays. So don't think because it's old, it's not relevant anymore. It's absolutely relevant. Then again, I would say my favorite book for learning about dimensional modeling is Star Schema, Complete Reference by Chris Adamson. A little bit better written in terms of understanding certain concepts than the Data Warehouse Toolkit. So it's amazing resource as well. Specifically about Power BI, I recommend two books. First one is from my friend Marcus Aaron Miller Jensen, Data Modeling with Microsoft Power BI. It's relatively new book. It was published a few months ago. Very comprehensive book, includes different examples how to model your data in Power BI with SQL, with Power Query, with DAX, so everything is covered. Very similar topics are covered by in the book from Sohail, Expert Data Modeling with Power BI. So again, a great resource for learning about data modeling. That was all from my side. So I will try to walk through the comments and see if there were any unanswered questions. But as far as I could follow, I think Pragati and Johnny answered everything. Okay, I don't see any questions. Joe asks, is this event yeah, it's recorded, it will stay on my YouTube channel, so yeah, I will leave it there. Thanks, Lloyd. Thanks. Any other questions? Any comments? Thank you all. Thank you for kind words. I really appreciate that. Thank you. Slowly changing dimension example. We need to leave something for the next webinar, so we couldn't cover everything. Yeah. Come back to Serbia. I will for the summer holiday for sure, if not before. Yes, I agree with you. It's killer to implement in Power BI. Yes, so slowly changing dimension definitely should be implemented one step upstream. Bitte gerne, Thomas. Thank you. Thank you, Pragati. Thank you so much. I really appreciate you helping out with this. Christian, yes, you know why Barcelona. We talked about that in Zurich last year. Okay. Then let's slowly wrap up. Thank you everyone for joining. I hope you got something useful from today's webinar. And yeah, one last thing from my side. If you're not subscribed to Data Mozart YouTube channel, maybe you want to do that. I don't want to force you, of course, but I think I'm sharing as much as I can on this channel, so maybe you will find something useful in the future as well. Thank you, everyone, and yeah, looking forward to seeing you at some of other webinars. Stay tuned and enjoy the rest of the day, wherever you are.